Okay, so welcome to the IEEE second presentation series on nuclear energy. Today we have a really extraordinary speaker, is Professor John Verboncoeur from the Department of Electrical and Computer Engineering in the College of Engineering at Michigan State University in the USA. Is going to tell us about plasma for sustainability. So I'm delighted to welcome John and to welcome, of course, all of you to this presentation. But before leaving John and giving John the platform, let me just introduce why we're doing that. So a few words. The need of clean sustainability and sustainable energy is, of course, clear today. As Ban Ki-moon said already in 2014, we know that energy is the golden thread that connects economic growth, increased social equity, and healthy environment. And so sustainable development is not possible without sustainable energy. So we are really looking at global energy system transformation. So this IEEE second presentation series on nuclear energy is brought to you by Future Directions, SUSTEC, NPSS, the Standard Association, and Planet Positive. And so it is really intended for a broad audience, not only the engineering and technical community, but also to those who are interested in the subject and which interest is also in the energy transition, clean energy, energy alternatives, nuclear reactor technology, and related topics. So this is a set of links that could be quite useful because it's pointing to the site where you will find recordings of past presentations and also to join mailing list if you're interested in future initiatives like this one. And there will be posted, I guess, on the chat a feedback for really getting your viewpoints and suggestions. Next talk is going to follow on the plasma. We really had a lot of plasma presentations this beginning of the new year, and it would be delivered by Professor Martin Nieto Perez. It will be the 11th of March. And he will enter more into the impact of fusion energy on the climate change landscape. Are we there yet? So he is an expert in plasma, and as you can see from his short CVs, he has really done quite a lot with plasma, from the kinetic modelings and design relevant to the insertion of fusion-based neutron sources in the nuclear fuel cycles. And so we will really enter, as you will see also in the abstract, a little bit more into the discussion of plasma for energy. But today's talk is devoted to plasma for sustainability. And you can see the remarkable CV of our speaker today, again, with a lot of expertise on plasma from all the different point of view, but of course with an eye in the applications of plasma to other fields than generation of energy. And in fact, as you can see also from the abstract, this includes really quite a gamut of other applications from material and semiconductor processing, industrial chemistry, environmental remediation, such as the breakdown of persistent pollutant like PFAS. And so let me just close with this and pass the floor to John Verboncoeur. John, the floor is yours.
Thank you very much. Okay. Sorry, I sent a request to share. Okay, too many windows. Here we go. Okay, so I think you should be seeing it now.
Yes.
Perfect. Okay, So I'm going to talk a little bit about a different use of plasma. As usually you hear about it in the context of fusion, but it's actually a huge economic driver. As Cinzia outlined, it is used in many different industrial processes, including the manufacture of semiconductors, more than $1 trillion of economic activity per year in that space. It's used heavily in lots of other areas, including things as simple as the saran wrap, the plastic wrap that you put on food containers, is processed with plasmas, believe it or not. And that makes it stick to the food better than the competitors' plastic. So lots of different uses. And I'm going to focus today on uses of plasmas which have environmental consequence. And I'm especially going to highlight some of the features of plasmas, why it's useful in these contexts, and why it can do some things that other mechanisms for generating chemistry can't do as well, and especially with respect to tying together green chemistry with green energy. So that's going to be my goal, is to make that connection. Okay, so I'll tell you a little bit about why this is important in a little more detail, and we'll talk only briefly about the fundamentals of plasmas, and then we'll talk about some opportunities around electrification, decarbonization, and in particular, we'll focus on Haber-Bosch. Haber-Bosch is the mechanism by which fertilizer is made, which is generally viewed as being responsible for supporting the growth in the number of people on the planet. And then also a little bit about a plasma-driven hydrogen economy, how we might transition into a hydrogen economy, which is quite related to the Haber-Bosch component as well. So first, a little bit about what is plasma. Plasma is the fourth state of matter, and so this is, the traditional solid, liquid, gas, and plasma is what happens when you continue to add energy to a gas. And so this makes it either partially or fully ionized. Many of the terrestrial plasmas that we do industrially are partially ionized. So they're using, for example, a background gas, and the background gas generates excited states and so forth, which can drive chemistry. And so we can actually manipulate chemical reactions that way. And they happen, as we view chemical reactions, as atomic and molecular collisions in the plasma world. But and the macroscopic scale, that looks just like chemistry, except it's done in this plasma state instead of in a gaseous or fluid state. So plasmas are typically defined as being quasi-neutral. I think of plasmas as anything with dynamic charged particles in it, freely moving about. And so I consider a beam to be a form of plasma, but it's very non-neutral. But I think that's just a more expansive view of things, that it doesn't necessarily have to be quasi-neutral. One characteristic of plasmas is that they can be observed in a huge range of time and space scales, over 10 orders of magnitude in both time and space. And so we have very, very short-lived rapid plasmas and very slow plasmas. And we also have plasmas at micro scales all the way up to astrophysical scales. So it's one of the elements of science with the biggest range of physical parameter space. Collisions are going to be important in the kinds of plasmas we're talking about here. These are between combinations of charged and neutral particles. They can be various states, excited states, and so forth. And so all of these things are very important. They can be with molecules as well. Molecules certainly play a role. They don't all completely dissociate in all plasmas. You'll hear me talk about cold plasmas. Cold plasmas are sort of in the 1 to 2 eV range. And to calibrate that, that's about the temperature of the surface of the sun. But it's also about the temperature of the electron gas inside of a fluorescent light. So it's, and you might say, well, why doesn't that fluorescent light melt? Well, the reason the fluorescent light doesn't melt is because the electrons are insulated from the surface. So the surface charges up negatively as the electrons impinge on it, and then shield the rest of the electrons from getting there. And once it's charged up negatively, the only electrons that escape are accompanied by an ion at that point. And the ion comes out with, let's say, around room temperature energy, maybe a little higher, because you can actually feel the heat on a fluorescent light, but it doesn't obviously melt the glass. And then the electron may come out with more energy than that, but the flux is so low that it doesn't heat the glass. So the things that are important in the interactions in plasmas are forces from electric and magnetic fields. They dominate. Generally, gravitation is not important. Exceptions might come in where you're talking about, for example, charged dust particles, large macroscopic things bigger than molecules being in the plasmas. So if you have a dust in the plasma, it will tend to charge negatively because the electrons are more mobile. And as I described from the fluorescent light surface, the electrons will charge it to the negative voltage level that it repels the rest of the electrons. And so as a result, charged dust particles may still have significant gravitation forces. One famous example is Millikan's oil drop experiment, in which gravitation forces and electrostatic forces play an approximately equal role. So boundaries are very important in plasmas, and this is actually my claim to fame in plasmas. Is in the early 90s, I developed the modeling tools to model bounded plasmas to be able to move from sort of theoretical, spherical cow plasmas, if you will, periodic plasmas or infinite plasmas to bounded plasma devices. And so I developed a lot of the early models to manage those, and especially to manage those with boundaries with realistic impedances, resistance, resistance, inductance, and capacitance to the outside world, which controls the flow of charges and so forth. So it has a significant impact on the plasmas. Debye shielding is sort of an internal shielding effect. It's actually the same effect as that glass charging up or that dust particle charging up. So Debye shielding is essentially what limits the flux of plasmas to various things that are near to them, that are bounding them. Sheaths are what we call that edge where you have that region that the electrons are repelled. We call that the sheath of the plasma. So we do worry about things like drifts, waves, and instabilities, and there are entire libraries of books written on these topics. We won't address those today, but plasma theorists, of course, live on these kinds of things, and so and obviously very important in plasmas. These represent things like how do we heat a fusion plasma? Well, we often use wave energy to heat a fusion plasma. How do we why are we unable to achieve fusion so far? It's instabilities. Things become unstable. In the picture, you can see a picture of the very familiar sun, and you can see a visualization of solar flares on that sun. And so the solar flares are essentially pieces of plasma that are breaking off. And these are essentially instabilities which quench when the instability evolves to a certain point. But these also can send out showers of energetic particles, very energetic particles, which can damage things like satellites, and even terrestrial instruments can be damaged. For example, the big power grid loops have and can be damaged by these big electromagnetic pulses that come from instabilities in the sun. So one of the big challenges in maintaining a fusion plasma is radiation losses. In the cold plasma world that we're going to talk about today, that's less of an issue. The radiation losses are less important and generally can be neglected to some extent. But the radiation losses in high temperature fusion plasmas, which are, let's say, 40,000 times higher than the cold plasmas we're talking about today, they can be very significant. And in fact, it's the reason that it's so hard to confine a plasma and keep it burning for so long is you just get a few impurity atoms, let's say some iron from one of the surface materials or tungsten or whatever, that gets into the plasma and it radiates like the mass to the fourth, z to the fourth, charge state to the fourth power, and they become fully stripped. And so the charge state for those heavy atoms is very large, so they radiate tremendous amount of energy. And so they easily can cool the plasma. It's the reason we don't have a critical accident possible in fusion plasmas that we have in fission plasmas, because if we actually had containment failure, that would immediately quench the plasma and eliminate the hazard. So we'll talk a little bit about electron distribution functions. And so I show here the Boltzmann equation. I'm not going to show too many equations, but I wanted you to see that there is a lot of technical detail behind what we're talking about here. In this Boltzmann equation, this variable f represents a distribution function, let's say, of electrons or ions. It's the probability of finding an electron or ion or any particle, a neutral particle as well, in a particular position x, at a particular velocity v at a particular time t. And so we often work with this distribution function, and it'll tell us a lot about what's going on in the plasma. For comparison, the air in the room you're sitting in is in a Maxwell-Boltzmann state, approximately. That's an equilibrium state, meaning just as many particles are increasing in energy as decreasing. So if you plotted this distribution function, you would see a straight line on a log plot. And that straight line would be at room temperature, whatever temperature your room is. And we're going to talk obviously about much higher temperatures than that, but the same concept applies. If it's in equilibrium, it'd be a straight line. And our goal here today is going to be to drive the plasma so strongly that we move it away from equilibrium. We change that distribution function, and that changes how that energy interacts with the cross sections, which are all energy dependent. And I'll show pictures of these things so you can get a better idea. But I wanted you to see the underlying equation. And this is, obviously a simple form of it. There's a lot hidden in things like the collision term and so on. There's a lot of physics behind that, but this is the essence. So plasmas are nonlinear. They can be non-equilibrium. They typically are non-equilibrium, especially driven plasmas. And so these are very interesting things. It's a nonlinear electromagnetic medium, so waves can mix in it. Maxwell's equations, which are, if you take the linear version of it, waves do not mix when they pass through each other. In a plasma, they do. So lots of interesting things are possible as a result. We solve a lot of this computationally. We solve, multi-million, 100 million particle simulations to understand what the plasma is doing. These are statistical representations of maybe a million times more physical particles, but we can actually get a pretty good representation with that smaller number depending on what's happening in the plasma. And these are some of the equations we solve, which should look familiar to you. That first equation is the Newton-Lorentz equation, relativistic Newton-Lorentz equation. So you can see the relativistic factor gamma, which is defined below with respect to the ratio of velocity to the speed of light. So obviously, as the velocity is small compared to the speed of light, gamma is 1. And obviously it can become very big at very high energies. And then the forces are just your standard electric force and magnetic force that you would find in a charged particle. We solve these by discretizing them, and I show a picture below of a common discretization. And the main point to understand here is that we solve something which is an approximation. So these of course have a certain accuracy to them, but we do that so that it's very fast. We chose algorithms that are low on memory, so they don't need a lot of extra memory to do. And so because we're solving tens or hundreds of millions of these per time step, and we're taking maybe a billion time steps, we've got to be fast with this so that we can get results on a reasonable time scale. The numerical algorithms introduce a lot of other things like instabilities. There are numerical instabilities as well. This is a very well-studied field, which has been studied since the 1960s. So there are lots of books on this, lots of articles on this. And we've actually developed some of these things more recently, but it's happened over that last 40 or 50 years. And likewise, we solve the field equations with a very common scheme for electromagnetic folks. This is the standard E-mesh. There are lots of other ways to do it. I don't want to say that this is the only one, but it's a common one. And so this is just looking at discrete electric and magnetic fields at discrete points in space and solving those by discretizing the Maxwell equations. Again, the point is not the details. The point is that there are computational equations. They all have approximations in them. And so those are all important things to be aware of. And we obviously work very hard to make sure the approximations are smaller than the physical quantities that we're actually looking for. Okay, let's get to the exciting stuff, the application stuff. So let's talk a little bit about electrification, decarbonization, and materials manufacturing. And so lots of different things are processed with plasmas, and I mentioned the semiconductor industry, semiconductor manufacturing. About 70% of the steps use some form of what I'll loosely call plasmas. I'm including that beams like beam lithography and so forth. So we call them dry steps. They're not using fluids chemical fluids to etch. And in fact, the plasma etching and the plasma implantation and so forth have huge advantages over the fluids because fluids suffer from surface tension. So that limits the feature size we can process, which means that the advances in the last few decades in semiconductor manufacturing, scaling this scale size smaller, have only been made possible by the use of plasmas and beams. So, and of course, light sources which come from plasmas and beams. So these are chemistry reaction dominant gas discharges. They're obviously partially ionized. You have industrially, you have a flow rate of gas in, flow rate of gas out. And so you can see in that middle picture a number of different processes and species. You have positive and negative species. You have neutrals, which might be excited states, ground states, etc. You can have molecules, and those molecules can have multiple states. Equally important, we actually have to think about in these molecular plasmas things like vibrational states. That actually absorbs a lot of energy to start atoms or molecules vibrating, absorbs a lot of energy. Likewise, rotation can absorb a lot of energy. So plasmas, including dimolecular things like oxygen and nitrogen, are very energy intensive. They take a lot of energy to break down, whereas noble gases tend to be easier because you don't have all those other energy sinks. So I also show in that cartoon some surface interactions like sputtering. Sputtering is when maybe a heavy particle like an ion or a heavy neutral particle impacts a surface. It can knock loose an atom from that surface. And often we deliberately do that, for example, to take a material, let's say in inertial confinement fusion, we want to make hydrogen targets. You take frozen hydrogen, you coat it with beryllium, and that beryllium is then the coating which you ablate when you add energy to generate an inertial fusion reaction. And so the coating is done by sputtering beryllium atoms off of a sputtering target and onto the workpiece, in this case, the inertial confinement target. And so other things that we can do, etch, so you can etch material. That's typically a chemical reaction, which is done not by impact directly, but rather by a chemical reaction with the surface by for example, excited state that brings energy with it to the surface that catalyzes the chemical reaction at the surface. And then you have reaction products coming off that get pumped away and so on. So ultimately, you can see some trenches there. That's sort of the bottom line in semiconductor manufacturing, is the ability to make those trenches smaller in width and deeper is sort of the key to the semiconductor manufacturing industry and its advances, and to make those trenches vertical. And so if you see real trenches, you'll see a lot of undercutting. They're not necessarily vertical. And so the extent that they're not vertical means that you may get more flaws in the semiconductor, and also limits how small you can go. So one of our goals in this, I talked about that distribution function earlier, is to control the distribution function and the energy flow in the distribution function. And the high level goal of that is to optimize the valorizable products of a particular reaction. So we'll talk a little bit about ammonia and some other examples. But generally, the idea is you can think of the chemical reaction chains in a plasma look like tree roots. They sort of branch everywhere and even reconnect in some places. And that's all the interactions between different reactions and the products of those reactions. And multiple things can feed in and out of those products. I'll show a very simple chart later so you can see what I mean. But it can be very complicated. So imagine sort of the biggest tree root system you can think of, with thousands of different root structures in it. And so we're able to modify that distribution function to cause energy to flow in the different reaction chain branches. And so we can move it from one branch to another. Now, it's not a huge amount. We can't control like 90% in one branch, but we can move it, in the margins. It's a few percent, even maybe 10%. But that's actually quite crucial. Because it means that we can increase the reaction products of the chemical reaction, let's say even 10%, but 10% more of what you can sell and 10% less of what is environmentally hazardous and has to be hauled away. We could, of course, run multiple iterations on that hazardous piece and reduce that as well if we were willing to expend the energy to do that. So the goal is to minimize those waste products while maximizing the desirable products. And so one of the big advantages of plasmas for this purpose is rapid startup. Traditional chemical processes are often catalyzed by, let's say, a platinum or some sort of catalyst. Nickel, for example, is often used. Those catalysts have to be heated up for about 2 to 3 hours before they become effective. So the challenge is with green energy to use in this space, If you don't have a continuous source of green energy, i.e., you have clouds or your wind is not DC speed, then ultimately you can't apply that very easily to traditional chemical processing because of that 2 to 3 hour thermal inertia. However, plasmas can turn on and off in microseconds and reach steady state certainly far faster than a millisecond. So that means that any sort of wind variations or cloud variations are easily within those time scales. And so we can turn these plasmas on when the energy is available, and they can easily turn off with no consequences, immediately turn back on, and within milliseconds be processing again. So this is really important to take advantage of that inexpensive green energy. For those of you in the green energy business, you know that green energy sells for between, let's say, order of 2 cents per kilowatt hour is the typical price that you can get for that variable green energy, because nobody can power anything consistently with it. You need lots of other ways to buffer it, store it, and filter it out. So that tends to cost, and so people pay less for the energy source. So we're trying to valorize that energy source. Now, coincidentally, the cost of energy from methane is also between 2 and 6 cents per kilowatt hour equivalent. So if we wanted to provide that heat with green energy, using the variable green energy actually puts us on the favorable side with respect to methane. So there's an economic argument as well if you could get around that thermal inertia process. So that's what we're trying to do. We're working with a lot of national labs and large chemical companies on this concept to scale it, to understand how we can scale it. And I mentioned before a huge scale model, which is done in big sheets around the saran wrap. Those are big linear plasmas that they run the sheets over like a big conveyor belt. And so it's certainly possible to make industrial scale low cost. That's a very low cost item, and plasmas are playing a role there. So it's certainly possible to do that. So one of the advantages of this concept is we can make these reactors pretty small. Let's say, a liter, the size of a liter or so, up to cubic meters. So we can really scale these things. And so the interesting thing about that is we could actually use this for distributed power generation. So if you have a 10 megawatt solar array, you could actually manufacture a modest scale chemical plant right there. And that actually turns out to be interesting for areas which are rural, for areas which aren't hooked up to the grid, so you can't even sell the energy back to the grid. You might be able to make chemical products there that are very useful in that space. So hence the interest in ammonia. Ammonia is a feedstock in fertilizer. It's a feedstock in a lot of other chemicals like plastics. It's also an interesting vector for carrying hydrogen for a hydrogen economy. So we're looking at tying all of those things together to build an ecosystem in which there's lots of value opportunities in that space. So thinking about this distributed production, chemical production, along with distributed power production, and connecting those together so that people who are deploying those kinds of systems have an additional way to valorize them. Also to think about future regulations for decarbonization, which we will surely have someday. Those will become important in terms of incentives to electrify. And so we want to get ahead of that and have technologies ready and economically viable technologies, so that switching over takes a certain amount of free energy, or think of it as a potential barrier. You get to the other side, and even if you're making money after the potential barrier, there's that capitalization step that can inhibit the speed at which things will change over. So we really want to reduce that barrier so that the economic reward is much easier to obtain. So that's one of our goals. So let's talk a little bit about industrial chemical processes, and I'll use the ICP initials here that's commonly used. These account for about 7.5% of total US greenhouse gases. I don't know what the number is in the rest of the world off the top of my head, but I think it's not so different. I think it's somewhat similar. Probably there are places that have significantly larger contributions, which pull the average up a little bit, but there are also a lot of places that don't have a lot of activity. But this is also an industry that represents 25% of the US GDP. So it's not something we can shut down. It's obviously of huge economic importance. So about 75% of those greenhouse gas emissions from those industrial chemical processes are from on-site combustion of fossil fuels, most typically methane. And so hence the interest in understanding how we can remove methane from both the chemical processes and Haber-Bosch as well. So lots of petrochemicals, ammonias and so forth, and steel and aluminum all require some sort of chemical processing or chemical interactions and are all very energy intensive using heat. Methane, as I mentioned earlier, is about 2 to 6 cents per kilowatt hour equivalent. And so we're in the right ballpark to compete with this economically. In fact, we're kind of on the favorable side of competing already before we've done any sort of value engineering. So that's good news. As I mentioned, the thermal inertia of catalysts mean that it takes hours, and so it's just not viable for a direct drive by most green energy sources. So a little bit about the electron energy distribution functions. Remember that Boltzmann equation, that F is the electron energy distribution function, the probability of being in any particular position, velocity, and time. And we're going to focus on the energy part of that to take all the velocities and wrap that into an energy and look at the energy probability. That red line in that upper left graph is your typical Boltzmann distribution. That's the equilibrium distribution. These are log plots, so the probability log of the probability is plotted versus the log of the energy. And so you can see that drops off rapidly at high energies. The high energy you can see below, the graph below is a set of cross sections. And the cross sections that are interesting are the green and red ones. The blue one is a momentum transfer, so it's elastic scattering. And so that's not particularly interesting. That just diffuses energy. But the other two are where the real work is done. It's where you form the excited states that do the chemistry. It's where you form the ionization that sustains the plasmas. So that's where the real work is done. And you can see from that chart that those things happen around let's say 10 to a couple hundred EV is the range of energies where those things are occurring. And so that means if you look at that upper chart, it's really the tail of the distribution, which is many orders of magnitude down from the peak of the distribution that does all the work. So you can imagine if you're using a plasma that's thermally heated in equilibrium, you're pumping a lot of energy into a plasma, most of which is just flowing out to the walls. And like any process that heats the walls, you then have to pay a second time to cool it. And the tail of the distribution is doing all the work. Imagine we could actually modify this plasma by driving it hard enough that we change the distribution function so that more and more of the energy is out in the tail. And so that's really our goal, is to really drive these plasmas so that the energy is in the tail. And that increases the reaction rate. Now, normally reaction rates in fluids, for example, in equilibrium, change are a function of temperature with respect to the Arrhenius equation, which I show here. And so that means that higher temperature means that you have a much faster reaction rate. And so this same kind of idea applies here, although it's not strictly the Arrhenius equation, it's a statistical version of that. But the main energy is done at those energy peaks of the cross sections, and so we're trying to optimize that. And we actually know a lot about how to heat plasmas from all of the research that's been done in semiconductors, all the research done in fusion. So we understand how to manipulate the distribution function with driving waves. So this is an exciting opportunity to turn that into a sustainable process that actually has economic benefit. So the basic idea is, can we put more of that energy into the part of the distribution function that will do what we want, and less of it in that thermal part that just heats things? And so that's our goal. You can see some non-equilibrium plasmas here, and especially think of that green curve on the upper right, the top green curve. That's sort of the thing we're shooting for, which we call a bump on tail. That's a bump on tail distribution where we've used electromagnetic energy to specifically heat the electrons in the tail of the distribution so that most of the energy input is there and much less in the lower end. And you can see if we can arrange that tail to be in the tens of EV range, that it's really hitting the peaks of those cross sections. And so that's crucial to accomplish what we want. And so this graph is in terms of Townsend. Townsend is a measurement that discharge physicists use, but effectively think of it as the electric field over the pressure. So higher Townsend means stronger electric field compared to pressure, which means we're driving the electrons harder, which means we're getting farther from equilibrium. And so that's what gives us that bump on tail, is getting farther from equilibrium. So as I said, for state of matter, 99% of visible matter is in the plasma state. So we're really looking at how we can take advantage of this. You see my more expansive definition of plasmas, but driven by electric fields. We can drive them with beams. We can drive them with photons. All of those things are possible. And we really just want to put more energy where we can get return on investment for that energy. That's really the goal. So this is the example I talked about with a very simple reaction cross-section set using argon. And I just wanted to show this simple difference, that a change in frequency, just changing the driving frequency, maintaining the same amplitude, you can see that different reaction chains. Let's see if I think I can do this. So hopefully this shows up for you. And so you can see the different reaction chains shown by these lines, and the different products are shown in these circles. And you can see different paths, so many of them reconnect and generate similar products. You can see the rates. We highlighted a few rates here, but if you compare each of these things, the only difference is driving it at 5 times the frequency, and you can see the shift in energy flow and all these different reaction chains just by that shift in frequency. Now imagine we drive it with a sawtooth waveform or a square pulse waveform and what have you. Those all make different changes in the energy. Now you can quickly see that there's an infinite number of options. So this is going to be a great problem for machine learning, to let it optimize what waveform should we use. And that optimization obviously also has to include how much does it cost to make that waveform. So we can choose maybe a variance of waveforms that get us 90% of the benefits at 10% of the cost to form that waveform. So the key to all of this is waveform formation driving the plasma and driving energy differently in the plasma, changing the cost structure of doing what we want to achieve. If we want argon plus versus maybe we want 4P because argon 4P etches a surface or something like that. So these are really our primary goals here. So let's talk a little bit about a use case for a hydrogen ecosystem. Imagine we could produce ammonia using green energy using this same plasma catalyst that I just described. Now imagine we replace the CO2 intensive Haber-Bosch process. Haber-Bosch is the process which makes, I would say, fertilizer that's used for essentially 50% of the global production of crops. And in more developed areas, it's much higher figure than that. But over all of the arable land on the planet, it's about 50%. It produces about 9% of the greenhouse gas load just for forming the fertilizer. So that's pretty important. That doesn't include the logistics of moving around the planet and so forth, just creating the fertilizer. And so this process essentially uses methane and a chemical reaction on methane to split the hydrogen out and the nitrogen out. And so, and the carbon out rather, and it produces a lot of CO2 as the byproduct. And this has been in place for 100 years now. And hasn't changed since then. And so the opportunity is to replace this with a green version. So getting, for example, the hydrogen from electrolysis rather than methane, and then using a reaction of hydrogen with nitrogen to form ammonia is possible after that. And so using green energy, because currently the barrier to doing this is the high cost of electrolysis. If we can use that 2 cents per kilowatt hour energy, that really makes this economically tenable. So the outcomes of this are ammonia for materials. You can also imagine the transport medium for hydrogen. I really like this idea because when I ask large auto manufacturers, why aren't they doing hydrogen fuel cell vehicles already? And they'll say, well, we have most of it. I say, what are your 5 main obstacles? And they say things like hoses, tanks, valves, gaskets, etc. So they're all mundane, mature technologies. And so I asked them, well, what's going to change that makes those work now? And they don't really have an answer for that. So the big challenge is really those standard things. How do you transport and store hydrogen? We can store it cryogenically and then transport it cryogenically, and it ends up costing 30 to 50 times as much, which makes it economically not viable. And so if we instead move it around as ammonia, which we already have infrastructure for, we have ammonia pipelines, we have ammonia trucks, we have ammonia train cars, we have ammonia ships. Um, and so all of those things already are used to move ammonia around. We have safety protocols for it and so on. Ammonia burns very slowly, so the hazard from ammonia is not an explosion. It's actually a breathing hazard, and it does quickly evaporate. But if you're caught, if you were in a big ammonia release and you don't have breathing apparatus, you could be fatal. And so it does evaporate within minutes, but not fast enough for you not to inhale it if you're stuck in that cloud. And so we do provide breathers, for example, in the trucks that transport ammonia. But nevertheless, we already do it. We already have the infrastructure. So the opportunity is using that and maybe using hydrogen cracking to separate the hydrogen out at the use point, or building fuel cells which transform ammonia to hydrogen and then can consume both exothermically. So those are all opportunities. And obviously, fuel cells can also go directly to electrical output. So a lot of interesting opportunities here. Thinking about hydrogen also as a use in steel, that's pretty obvious. And then finally, hydrogen to upgrade biofuel. We're working on that here at MSU to hydrogenate biofuels, looking for sustainable aviation fuel. And this is a JP8. This is a typical jet fuel. So this is a real interesting opportunity to have impact on another form of transportation, which is a lot harder to electrify. And so that use point, the cracking at the use point, is probably too large and complicated. It takes about a cubic meter to do that at speed. And so that's probably too large for a consumer vehicle, but for any commercial scale vehicle of the variant we talked about, it could be a big game changer. And obviously the biggest game changer is on ships. Ships burn worse than crude oil, and it's incredibly cheap, but it's incredibly polluting. And so if they had the ability to store energy at the density of ammonia and were able to then consume that energy, it would be a much better alternative for the shipping industry. Okay. Another use case is around SF6. SF6 is another forever gas, which is used in the power industry, and in particular in the transmission and distribution industry. This is the gas that's used in high tension lines because it reduces or increases the breakdown voltage in those lines. So you can go to higher voltage. Because of the build out of global power distribution systems, SF6 has risen dramatically. It's about 23,000 times more effective at trapping heat than carbon dioxide, so that's a big deal. And it has a stable lifetime of about 3,200 years, so much more impactful than CO2. And so you can see this is a really critical gas. Even though it's a fraction of a percent in the atmosphere, it already constitutes about 10% of the greenhouse gas burden, and that's rising rapidly. You can see that the emission has increased from 7.3 to 9 over the course of about a decade. So that's a rapid growth of about 25%. So this is really crucial to pay attention to. National labs are looking at replacing SF6. They're looking for alternate gases. And we're using this same process that we use to study these other reactions to study how we might make a gas which mitigates breakdown like SF6, but doesn't trap greenhouse gases. So we're hard at work looking for those kinds of things as well. Okay, a lot of other plasma applications. I'm just going to list them here. For example, PFAS, NOx, hydrogen sulfide. Hydrogen sulfide is a big deal because a lot of the remaining hydrogen, a lot of the remaining reserves of oil on the planet are contaminated with hydrogen sulfide. And so when you extract them, you have to separate out the hydrogen sulfide, because otherwise, if you burn that oil, you end up getting sulfurs in the atmosphere, which have lots of bad effects. And so, so we're looking at that as another pathway is can we, for hydrocarbon industry, separate out the hydrogen sulfide more efficiently. Right now, it's again another methane burning process, of course. And so reducing the environmental hazards in semiconductor manufacturing, there are a lot of hazardous gases used in that business as well. So finding alternate gases with less environmental impact is also important. One of my favorites, agri-food systems. I mentioned Haber-Bosch already. food sterilization and so on, lots of uses for plasmas there. Plastics remediation is becoming an increasingly important area. Can we actually neutralize plastics that, microplastics, for example, that find their way into the food supply and therefore into humans? The average human on the planet has about enough plastic in their brain alone to form a plastic spoon. So if you're ever, caught out in the woods and you have a can of soup but no spoon to eat it with, it's right there in your brain. You just have to figure out how to extract it. Surface bonding to replace some adhesives. So there are a lot of environmentally hazardous adhesives used in manufacturing, and understanding how we can use plasmas in surface bonding is an interesting, and obviously many, many more. So I'm going to wind up here with just a slight review. And so we talked a little bit about industrial chemical processes, replacement of methane heat sources with pulse plasmas or otherwise interesting waveform-driven plasmas, thinking about distributed ICP to manage the large rural areas that could definitely benefit from green energy generation if it could be better valorized so that they weren't waiting 20 or 30 years for return on investment. If we could bring that horizon down to 3 to 5 years, that would make it really exciting. It would be a subsidy-free opportunity because it would have that quick ROI. And then also understanding we haven't optimized most of these processes. We have a lot of opportunity in modifying waveforms to understand how we can do even better. So lots of federal agencies are getting interested in sponsoring this work. I've been pitching to them for a few years now, and national labs are starting to work in this space as well. And we're looking for industry and government partners to continue to develop this. And I think the industry input in this is going to be very important to productize it. It has to be more than a lab experiment. It has to be something that you can build at scale quickly, requires very little maintenance, easy to operate, et cetera. So big opportunity there as well. And ultimately, we want to see this produce not just sustainability, but net economic benefit along with sustainability. And I'll stop there. This is my shameless plug for SmartAg. I had to get that in here somewhere. So if you follow this URL or you follow this link, it'll take you to the SmartAg website, and you can sign up to be on our mailing lists and so on to learn more about SmartAg. So I encourage you to do that. Jinzia, back to you.
Thank you. Thank you very much, John. Wow, there is so much information here and so interesting. And we have a couple of questions here which have been posted, a question and a comment, in fact. And then I will try really to pass through some of the questions that I have, and there are many. So the first one is from Charlie, and is asking, what reactions depend on thermal power or total energy and peak voltage? Dielectric breakdown is often due to peak voltage, but some reactions are just due to the local heating.
Yeah. Yeah, good question, Charlie. So most reactions are not actually due to heating per se. It's still the tail of the distribution. So imagine just a very simple reaction like oxidation of iron. That reaction still has a significant energy, a significant EV level energy, which you can imagine is, so one EV is roughly 11,000 degrees C. So you don't have very many room temperature particles operating at that energy. However, they can still interact because there is a tail out there, and so there is a probability that every few seconds you get a reaction or something, and that's why oxidation is such a slow process, is because it happens very slowly. If you heat it up, then it will happen much faster because when you heat it up, you've got more of those particles at the higher energy, so the reactions happen more frequently. And so our goal is to add that heat specifically to get into that reaction regime. Dielectric breakdown is a little different in the sense that, it is sort of an interaction, but it's often a cascade, and it's often, for example, secondary electron emission from a surface, which is not really a chemical process. It's really more of a physical process. So it is somewhat different than the chemical process we're talking about here. The peak voltage is important because the peak voltage determines how high of an energy you can get. Basically that sets or that drives the energy higher. So if we increase the peak voltage and keep everything else the same, obviously we're going to shift that distribution to a higher energy level and we're going to get a faster reaction rate. Now, of course, we could shift it too far and actually go past the reaction peaks and start getting a slower reaction rate as well. But that's hard to do with heat. It's much easier to do with targeted electromagnetic energy that's targeting a small range of velocity. If you've got 100 watts to put in and you put it in as heat, you basically put 99 watts into heat you can't use and 1 watt into heat you can use. If you use microwaves, you can put maybe 10 watts into heat you can use and 90 into heat you can't, or so. And maybe you can do even better with beams or with a very special, maybe a non-sinusoidal microwave driver. I might be able to do a lot better.
Thank you. Another question from Simon Sunatori is regarding ammonia cracking at use point for hydrogen fuel cells or hydrogen combustion. He's asking,
CJ, I see another question about hydrogen being small. Did you see that one, Almasano?
right, yes, I saw it, but somehow it looked more like a comment.
Oh,
But if
okay.
but if you want to address that first, it was
Well, that's
first.
why so I'll just say very simply, that's why we're looking at ammonia to avoid this problem.
Exactly. So I think what I would wanted to conclude with Mesano, with Al
Yeah,
Mesano, that yes, we all agree that just transporting hydrogen, it is not really
yeah,
a good idea. And so finding
right.
alternative way like ammonia, it is definitely a good idea. So
Right.
I think, well, okay.
And I
So,
don't
so
want to assert, I don't want to assert that for space things because you might have very different economic margins in space. And I don't know the exotic materials that NASA might be trying for this. But I'm sure it's still a problem in space. It's not trivial, but on Earth, it's just economically not viable. We don't have a way to solve this.
thank you. And sorry, Al, I didn't really mean really to bypass you. I just wanted to leave you at the end as a really the cherry on the cake. And so you see here then the question of Simon, let me just read it. Is it feasible to use ultraviolet light for electromagnetic hydrogen generation by ammonia, photodissociation, not necessarily plasma?
Yeah, it's surely possible. The question is whether the economics adds up. So the challenge with anything photo is the efficiencies are not usually terribly high. Now, granted, we're certainly seeing the increase in efficiencies in LEDs. And so the question is, can you produce enough LED power to accomplish this task at a high enough efficiency to make it economically viable? And I actually don't know the answer to that without doing the calculations, but my gut instinct is it's probably going to be difficult. But I bet someone out there's trying it, so you can probably find it in the literature. Sorry, that's an incomplete answer, but this isn't something I've tried, so I can't really speak explicitly to it.
Okay, so I can see that there is another question from Charlie. The Haber-Bosch process is the most efficient in a centralized production process, but the plasma approaches that you mentioned are better for distributed systems. The question is, how can one compare the economics of the two approaches?
Yeah, so Charlie, let's use an analogy. Let's think about farm products since we all like to eat. So if you think of locally produced farm products in your local area, it might cost a little more to produce them because labor costs are higher, what have you, but the logistics costs are a lot lower. The refrigeration needs are a lot lower. The spoilage is a lot lower. So you have to think of the system. What is the system effect? So the distributed manufacturing even if it is even if it's not directly winning on cost per unit compared to Haber-Bosch, because methane does remain relatively cheap. Where it could win is if there's a local use case for it. So if you're generating it where you use it, you reduce the logistics, and the logistics, as we talked about in hydrogen, are pretty ferocious. The logistics for ammonia less so, but still not insignificant. And so if you have local uses for it, that might be a mechanism. So if you're doing it, for example, in an agricultural environment and you're immediately using it for fertilizer, which we're actually doing here at MSU. We have anaerobic digesters that produce ammonia and natural gas, and we're using those locally rather than transporting them and storing them. So they're used, for example, for fertilizer in the fields in which the cows it's in a dairy, it's in sort of a research dairy. So we use it in the fields there, and the natural gas is used for heating the cow barns and so forth. In Michigan, you have to do that. So those are all things that local use can also be an economic impact to consider. So you have to think of the system level.
Thank you, John. So I have a list of questions here, but I think I will just ask one. Um, how far are we from green aviation fuel?
Yeah. That's a good question. I think we actually can make fuel that works at that level now. And again, it's the economic question. Can we do it at scale? And can we do it for a lower cost than a hydrocarbon-based JP8? And so we're still working on that. We're actually shifting from typically it was done with biomass. And if you've ever heard me talk about this before, you know I don't love biomanufacturing processes that need to scale. They're great for pharmaceuticals and things you need small volumes of. But when you need to produce millions of gallons, I don't love the fact that you turn up the temperature in a chemical process and the rate increases exponentially. You turn up in a biological process and it essentially drops off a cliff pretty quickly. And so that's my concern is that it's hard to scale. You need just huge areas of land, just huge volumes of reaction chamber, and it can't really be volume. It's got to be because you have to extract the heat from it, you have to cool it, and so it has to be sort of a large planar area that you do those biological processes in. So I don't love those because the rates are so low. But I do like the idea of taking, for example, silage and other things that were normally going to be waste and extracting, for example, the oils from those. So you can actually extract oils from that silage, and then you can use those oils as the basis for a biofuel because it's waste and it's not biologically being processed. It's really being processed in other chemical ways or even just heat ways. And so hydrogenating that is an interesting option that we're looking at to increase the scalability. So everything
Thank
you're going to hear economics is always part of this because we're all
Of
kidding
course.
each other if we don't bring economics into it.
No, of course, that's clear. So there are another couple of questions I can see here. So Daniel Peters, as you see, is asking, FS6 is a very heavy gas. When released, it buries deep into the soil. It
Mhm.
doesn't last long in the atmosphere. How can SF6 be a greenhouse gas?
SF6 lasts very long in the atmosphere, about 3,200 years.
So it is not really true that it would really be buried in the soil. It
Oh,
wouldn't
you mean
come
if you
out.
could? Yeah, I don't know the answer. If you deliberately sequestered it in the soil, would it remain confined there? I don't know the answer to that. But the problem with SF6 isn't that we have spent gas that we're disposing of intentionally. It's that it's gradually leaking out of all the transformers around the world. And so we don't have control of the leakage, and the leakage rates are so slow that it's not easy to detect and capture. And so the problem is not a controlled one where we could sequester it easily.
Right, the sequestration and the fact, of course, that this life is really
Yeah,
very long in the atmosphere.
right, right.
So there are many companies making green fuel, and they also make alcohol from thin air. This is Charlie.
Yep. These are all absolutely things that are possible. I've even met with some of these companies, and the real question is how to scale them up and how to make them economically feasible because many of these operate at a loss to make their fuels because the inputs are the energy input is higher. I mean, for example, the example Charlie mentioned, yes, you can make from thin air quotes. I mean, you need the hydrogen from somewhere. There's not much hydrogen in the air. But you need a source of hydrogen, which is often methane in many of these processes, which we're trying to avoid because the outcome of that is often CO2. But it doesn't mean you can't get around it. You could, for example, create other compounds with the carbon, carbonates or something like that. Then you'd have to introduce some other components to it, and the energy of the reactions might be significantly higher. So we have to think of the cost structure, not just the products. Again, it's an economic question.
So we are taking the hour, and I see that Al is being surprised to hear that FS6 is a significant greenhouse gas. The usage volume seems to be insignificant when compared to CH4 and CO2.
That is all true, but it's dwell time in the atmosphere. So if you release an atom of CO2, it has a certain dwell time in the atmosphere, and so we're not calculating its current, sort of a snapshot of its effect. We're calculating a lifetime effect. So
Lifetime.
every atom you release, you compare it to an atom of CO2 in its lifetime. We do that with lots. So for example, methane is about 40 times more intense greenhouse gas than CO2 based on that lifetime analysis. Now, methane has a shorter lifetime in the atmosphere, but it's much more intense than CO2.
Okay, and so I think that with that, I'd like to thank the speaker. So thank you very much, John. It has been really a real pleasure and a lot of very interesting information. I also would like to thank all the team, the organizers of the second seminar series in nuclear energy, and the IEEE staff for helping with that. And of course, all the people who are joining in and listening and asking very interesting questions. So thank you very much. Please mark your date is the 11th of March, and we will have the next chapter of this journey with, again, plasma, but really focused on the generation of energy with Martin Nieto Perez. So thank you very much. I'm looking forward to seeing you all in 3 weeks from now.
Thank
Thank
you,
you.
Shinji, and
Thank you
everyone.
very much, John. It was wonderful.
Take care.